Welcome to Unmanned Experts online training courses. This is the UAS Basics module designed specifically for individuals who are looking to enter the civilian UAS market as it develops and grows around the world, and to bring them up in this module from a very low entry standard to understand some of the concepts and the terminology that we'll be using throughout the rest of the course. It will literally answer what the U in UAS stands for, and the answer may actually surprise you. So welcome. Thank you again for purchasing one of the Unmanned Experts training modules. Just take this opportunity to remind you about the end user licensing agreement, which you've signed on downloading. This allows you and you alone to take the course. Please, if you need to reread the standard terms and conditions, they're accessible here, or email us at oltraining@unmannedexperts.com. Enjoy the course. Many thanks. A quick refresher for those who haven't done much online instruction recently. The slides are obviously narrated, but this is optional for you. There is a mute button at the bottom. Feel free to use that at will and stop and rewind or fast forward as you see fit. You can quite happily read the slides if you need. There are a number of videos embedded within, and you can click on those with the mouse and get them. They often enhance the point. And there are a number of storyboards as well, which should actually give you a bit more of a personal feel from the instructors concerned. Again, entirely optional. As you work your way through, you'll find a number of quizzes. You'll be scored at the end of these, you'll get the results at the end also. So this is just to check understanding. And finally, if you do have any questions throughout the course, then please note the slide number and email us at oltraining@unmannedexperts.com. Good luck. Hi, a personal welcome from myself, Kevin Gambold, the Operations Director of Unmanned Experts. I'm one of the instructors on the courses, and you'll see several other faces here, other voices as you work your way through the various modules. Anyway, I thought we'd give you a little face-to-face for me, and the other instructors can also give you their background, or it can be found on our website. So anyway, welcome, enjoy the course, and if you have any questions, you can come directly to me. All the best. The UAS Basics module's goal is to make sure we're all singing off the same song sheet for the rest of the course. So we will all understand the various terms and definitions. There are an incredible number of three-letter abbreviations out there. So we'll start by looking at what makes up an unmanned aircraft system as opposed to just an aircraft. We'll look at the difference between RPAS, UAS, beyond line of sight, all the TLAs, and then we'll see all the different ways that they're currently being operated in theatre. So visual line of sight, radar line of sight, beyond line of sight, etc., as well as the larger piece, how processing, exploitation, dissemination goes on, and allow you to form your best, your own opinion of the best fit arrangement. So that's the aim. Off we go. Okay, not a great believer in reading a scope slide to you, so these are the items we're going to cover, and we'll see them one after the other as over the next hour. Okay, enjoy. So what do we really think of these unmanned aircraft or drones? These cartoons you can see here are very recent, and they epitomize the widely held stereotypes of what UAVs are up to these days. I'd like to say they're entirely untrue, but there are elements of them that is correct. However, what we'll find out later on during these courses is that this is more the type of UAV operators that we're going to be seeing. And each one of these, although they look very different, are a UAV pilot operator, remote piloted aircraft system operator in their own right. Of course, it's always good to know where we are before we try to go where we're going. So we'll get a quick baseline quiz to see how many of you out there have been following the newspapers as far as UAVs are concerned. Don't worry, this doesn't affect the final score. Okay, now to get you back on track, focus our minds on the UASs that we're about to be studying. A brief video here just to look at some of the civilian UAVs that are out there that have been used. In this, you'll see a Sky Y, a Metaplane, and a Falco. See if you can spot which are which. And it's a bit of a promotional.
Però probabilmente hanno ristabilito la connessione. Paolo mi parli con tutto. Terminato, perfetto. Leggermente a destra. Leggermente a destra. Perfetto.
Let's get on with the meat of the brief then. So we started by saying we would find the definition of the unmanned aircraft system, and this is how it stands apart from the manned platforms, which you could buy a Cessna C-152 today, and that's pretty much all you need to do. Gas it up, stick yourself in there as the pilot, and go. If you bought yourself just a UAV, an unmanned aerial vehicle, then you'd have something to put on the lawn, but that's about it. So the entire system is required. That is, as you can see here, top left, the unmanned aircraft. And often these systems are bought with a number of aeroplanes. So you don't actually, when you buy a Predator UAS, for example, you will end up with 4 aeroplanes or air vehicles. This example, you actually just get the one Select Scale Air Falco. But you can see with different systems, you get different arrangements. Very important is the aircraft itself is no use without the payloads attached, and we'll see in the payload module later that really the aircraft can be seen as a payload truck. So you have to bear that in mind. We need often EO, IR, sensor balls, for camera full motion videos, radar, electronic information as well. So all of these different payloads to be attached. You can't go anywhere without, if we go bottom right, the ground control station. That is the cockpit, and it can be as small as an iPad or as large as these sort of internal ground control stations that we're seeing here, known as GCSs. You need the pilots, and often the pilot and some form of sensor operator sat next to him. So they're the operators. And then you need that cockpit to talk to the aircraft, and that is through a number of dedicated data links. And they can be, as this one is, a line of sight radio data link, or they could be beyond line of sight. Some of them, the smaller ones, use Wi-Fi. And then finally, you need the support equipment. In larger systems, they can take off from the runway. Smaller ones can be hand launched and just land at your feet. But this one, for example, can either be runway launched or it has a catapult. So, and they're pretty specific systems. So you need all of these pieces to make an unmanned aircraft system, and make sure you check you have all those bits when you buy one. So let's take a look at a number of the systems, starting at the smaller end then, and these are taken at random, but they're quite good examples, I think. First one is the Scout, made by Ariane Labs up in Canada. It would be classed as a micro UAV, weighing about 3 pounds all in, and we'll talk about the classifications and the different types later, but basically very much at the small end. It's a ground VTOL, vertical takeoff and land, or you could actually launch it by hand, and a quadcopter. As you can see, it has 4 independent electric engines, and they're run by lithium polymer batteries, which has some of the latest technology and gives a 25-minute endurance. As you can see, it's simply a short-range visual line of sight system designed to basically put up over your own head and, you know, up to about 500 feet above you. The whole kit will cost you just shy of $150,000 US. And you get a payload, which you can see in the center screen there, and there are changeable payloads: infrared, IR, high definition, etc. Now, a closer look at what that $150,000 will get you, and bear in mind that's the cost of the high end. You can walk away with one of these systems and most of the parts for just under $100,000. Like that makes a difference. So you would get one air vehicle, otherwise known as a UA, an unmanned aircraft, or a UV, an unmanned vehicle. You can see it in the center picture here. It is the body, 4 arms, 4 legs, and 4 motors. And the battery pack, as you can see to the top right, is very easily swapped in and out. And you'll get 4 of those and a charger. So you can fly one of these for 25 minutes, land it, replace the battery immediately, and off it goes. And we'll see how simple that is in a second. We're talking about a local area, so no complicated data links. It runs purely off a Wi-Fi system, which is attached to your controller, your ground control unit, ground control software. So you have the antenna and what is effectively a tablet with its own indigenous software that's designed for planning the routes, for obtaining the video feed from the payloads. All of this comes in a mission case. And then, of course, you get your payload. Now, the good thing about this is the payload is 3-axis stabilized, so it's not just flying above you with a fixed angle on the camera. The camera itself can be rotated using the ground control unit, focus, zoomed in. So, and it's a very effective piece of kit that way. But you have to change out the payload. Obviously, at that size, you're not talking about something that it can do both daylight and nighttime, or low light, or have some form of lasers. I mean, it's a very low-end payload, although good quality in whatever one you select. Again, equally interchangeable, which we'll see in a video in a moment.
This is the Arion Scout, a man-packable, easy-to-use unmanned aerial vehicle. Weighing just over 3 pounds, the Scout can be deployed from a backpack in under 2 minutes. Featuring a patent-pending touchscreen interface, a single user can pilot the system beyond line of sight while remaining focused on a mission. With only 4 moving parts and a ruggedized all-weather design, it can be assembled without tools. With a suite of gyro-stabilized payload options, cameras snap into place, allowing the vehicle to be quickly reconfigured for day or nighttime operations. The Scout's networked architecture features encrypted communication, control, and storage. The geo-targeted camera automatically tracks the subject. Its impressive specs include a 3-kilometer range, ground speeds of 50 kilometers per hour, and an 80 kilometer per hour world-leading wind gust capability, making the Scout the platform of choice for tactical intelligence operations.
Right, we'll now step up in scale. We're moving on to a fixed wing, a slightly larger platform called the Arcturus T-20. It's the largest of a family of Arcturus products built in the US. T-15, T-16, very popular, simple to use, but an order of magnitude more complicated and expensive than what we've just seen. And yet, at just under 180 pounds, it can carry 60 odd pounds of payload, which is extremely important. So it can be quite capable that way, but it still is classified as a small UAS, and we'll come on to those later. Anyway, it is rail launched, as we've seen here, and it lands on its belly. It has a carbon fiber belly to just scrape along the grass or the runway, but it has a pneumatic launcher to get it airborne. Small piston engine, which gives it an enormous endurance, though. 16 hours is incredible, really, and we are talking about a different capability here. It is effectively not a visual line of sight, but a radar line of sight system. So this is designed to operate in the local area using an internal ground control station rather than standing outside. You're in a box with a proper data link set up, and each one of these, as you buy the pack up, we'll see what you get, but is just shy of $1 million US. Okay, so as you get your Arcturus T-20 kit back home, when you unpack it, this is what you should find. 2 aircraft vehicles, AVs, probably with the wings removed. You can build them up as required. Engines, spare parts, etc. You should have a payload. Now, the payload shown here, it's quite a high-end, both daylight and infrared turret that is retractable, therefore the aircraft can still land on its belly without damaging. But with 65 pounds of capability, you could have no end of options. And in fact, in the center lower photo, you can see a T-20 configured with 2 drop tanks or 2 drop payloads. And we'll come on to in the payloads module later, the other options. You'll need some form of C-band ground control, ground data terminal, GDT. That's basically the data link to communicate. And if it needs to reach out to that 50 nautical mile maximum, then it needs to be quite substantial, maybe on a pole, etc. And you need the such as the launcher, any landing equipment such as the net shown here as one of the aircraft are landing in that, or as I said, it could belly land. And then most importantly, you need 2 ground control stations for both an EP, an external pilot, which we'll see in a moment, and an IP, an internal pilot. The internal pilot is shown top right here. You can see the screens that he's utilizing, and he's got mouse, keyboard, joystick, etc. to control the payload and the flight path. The external pilot is stood with a traditional sort of remote control powered to a considerably more powerful data link so that he can pick this aircraft up, and he flies it into land manually. So you'll need these two aspects. Right, now on to the big stuff. This is one of the largest, not actually the largest example, civilian used UAS on the planet. So the RQ-9 Alpha Predator B. It's a military cousin known as the MQ-9 Reaper. And it's US built, General Atomics Aeronautical Systems out of California. It's a monster. It's about nearly 65 feet wingtip to wingtip, really. Weighs just over 10,000 pounds. Anyway, it's used by the Customs and Border Patrol in the US, the Coast Guard, and the Italian Air Force also have the RQ variant, but they've just recently weaponized it into the MQ. So, as I said, at that sort of size, it's runway launched and landed. It's treated just like a normal aircraft. It's had a turboprop engine, which, given the right sort of payload, gives it 20 hours endurance, climbing to potentially, if you read the marketing material, 50,000 feet. And most importantly, that big dome on the front is a satellite dish. It works beyond line of sight. So we're not looking at any line of sight restrictions. It's based, you're flying the controls via a satellite pretty much anywhere in the world. Obviously, it would land on the runway. And each one of these will set you back fully loaded about 30 million. But if you want to get the whole kit and US dollars, 155. And to be honest, there's no way of really classifying that because satellite links, satellite costs, support programs, they all add to the price. But anyway, certainly an order of magnitude above the others. Okay, the Predator B Reaper type systems. The smaller brother used to come, the Predator A used to come with 4 AVs. Initially, the Reaper, the Predator B would be sold with 2, but I believe later reports from customer board protection suggest that they are buying 4 per system, which makes sense when it comes to logistics, which we can discuss in another module. The aircraft themselves, then, as I said, unladen, they probably weigh about 8,000 pounds. Then you add the payloads. We see at the bottom left here, this large one is pretty typical, known as the MTS Bravo. It's electro-optic, infrared, low-light television. It has a laser ranging designator. That's what all of those acronyms stand for. And the TSAR is its tactical synthetic aperture radar, which it's also fitted with. It has a number of data links, both if you go top right, the C-band line of sight antenna used for close-in work and takeoff and landing. And then it has a KU-band satellite antenna, which is an enormous piece of kit that allows you to take it beyond line of sight. And then you'll get the big box that it's all kept in, called the internal, the ground control station. And in that, you can see a fairly typical set of racks. You have a pilot and a sensor operator in this case in there, and we'll look closer at the racks during the components phase of the brief. This video is just designed to show you some of the airfield maneuvering characteristics of the larger UAVs, and to give you a feel for their scale and size. So it's all, in this case, the Custom Border Patrol Predator B, but you can see that it operates in an identical manner to a manned aircraft, and a fairly sizable one at that. So as you can see, it has to taxi, take off, obtain all the same air traffic control clearances, etc. I'll leave this with you. Now we start the next section looking at the terminology that we're going to use throughout the rest of the courses, and to bring you up to speed on some of our definitions and 3-letter abbreviations. In this phase, we're going to overview a large, in this case, a medium altitude, long endurance Predator type operation, and all of the different terms that are used in it. This basically encompasses many of the aspects that we'll see in almost all systems. So we're using this as the example. So let me walk you through the page that you look in front of you. On the left-hand side, you have your ground control station in CONUS. In this case, that stands for the continental US. There's a satellite link in the center, and the aircraft is flying on the right-hand side in theater. And we'll discuss each of the links and what the names of the various areas are. So let's start with, on the right hand side where the aeroplane is, this aircraft in theater is launched and landed by a team called the Launch Recovery Element, the LRE. That's a small deployed team of engineers, pilots, operators, and they refuel the aircraft, rearm it, kick the tires, light the fires, get it airborne, and then they would use a line of sight data link to control it. That line of sight data link for commanding the UAV is traditionally known as a uplink, a UL uplink, line of sight uplink for command, and they get all the video and the payload information back on the line of sight downlink, or DL. So for a launch recovery element or people in theatre, line of sight uplink and downlink. And that downlink can also go to that little chap lying in the mud who is looking at Rover, which is a kind of a handheld video monitor. Right, so when the LRE have finished operating with it, they hand over to our chaps on the left-hand side, in this case America, who are the MCE, the Mission Command Element. And traditionally these would be doing the long endurance stuff that goes on for days, basically, with these larger platforms. The MCE control the aircraft via a beyond line of sight link, and their command of it is known as the command link, the CL. And they receive the video feed back through the satellite on what's known as the RL, or return link. So line of sight is uplink, downlink, beyond line of sight, command link, and return link. This is traditionally accepted across most of UAVs. Finally, now, if we look at the bottom left, all that video feed that goes into the ground control station, or GCS, is then fed into what's known as a PED process, a process exploitation and dissemination link or chain. And that's where it goes to the headquarters, in this case the White House, and all the image analysts can have a look at the information that UAV is providing. So that gives you an overview. Let's look at some specifics. So let's expand a little bit on the TLA three-letter abbreviations that we're going to see throughout the course, and there are plenty of them. And this is also the place that we look at a real definition of UAVs. Initially then, UAV, traditionally known as an unmanned, but can also be uninhabited aircraft system, air system, or air vehicle. The more modern term is now RPA, and we'll come on to some of the specific definitions in a moment. Remotely piloted aircrafts or an aircraft system. MCE and LRE we just looked at in the last slide. And further down, or an overview of the entire process is known as TCPED, tasking, collection, processing, exploitation, and dissemination. And hopefully throughout this course, you will see a piece of each one of those. So, but that explains the entire cycle of asking a UAV to do something, it doing it, and then you doing something about the information. Command link, return link, uplink, and downlink we've been through painfully in the last slide. And we saw Rover, or RVT, which is a remote video receiver or remote video terminal, where we can beam information down to troops on the ground. On to the next slide. So slide 2 of our TLAs, and bear in mind that in our course book you have a list of acronyms that stretch to over 200 or so, is looking at a rather thorny issue in UAVs, or RPAs, concerning the personnel, the positions of the crew and people associated, what they're called and what their duties are. The more common ones then, PIC, pilot in command, very akin to how they have it in manned platforms. We also have a PAC, a pilot at controls, which would indicate somebody, almost a stick monkey, someone at the front that's flying the UAV but may not actually be the PIC, almost like a co-pilot in some respects. An IP normally would be seen as an instructor pilot. Here it's an internal pilot, someone inside a normal ground control station, GCS. And an external pilot is stood out on the runway in all weathers, landing and taking off an aircraft that requires that. Another term for all of these chaps is an air vehicle operator, or chapesses, and this is commonly used by the Army, but it's normally for the piloting type position. On the other side of a ground control station would be the sensor operator, the SO. He normally operates the payload system, and the armies often refer to them as MPOs, mission payload operators. Overseeing all of this, you may have a mission commander, or MC, and assisting them or the crew is a number of IA's image analysts. or other intel folks who are normally also coordinated using a mission intelligence coordinator. And between these 4 or 5 people of various names, they all produce a crew. So we'll use this last TLA slide to throw together some of the hodgepodge of abbreviations that we will probably use, and I may add more as we go. Or ISR is Intel Surveillance and Reconnaissance. ISTAR includes target acquisition, and we'll see this is one of the primary roles of any UAV, so you hear it an awful lot. As well as near real time, and this is effectively what differentiates picture-taking aircraft and missions from UAVs, which can beam the information down to you immediately. So in near real time, you will see exactly what's going on. And of course, UAVs specialize in full motion video rather than still photos for the most part. So FMV is something you'll also hear. As we get into the legislative aspects during the course, you'll hear a lot about sense and avoid, SAA, otherwise known as detect and avoid, and it can either be air or ground based, so ABSAA or GBSAA, and that depends on where the sensors are located, obviously. Again, into the human factors, you will hear HITL and HOTL, human in the loop, which means that the pilot is, or the manned individual is operating the aircraft and is part of the decision-making loop, or on the loop where he is perhaps just supervising a more autonomous aircraft. So, and part of that interaction you will hear often referred to within the ground control station or GCS is the HMI, human machine interface. In other words, the cockpit and how the controls are. And we'll look into aspects of that in human factors. Finally, and we'll come on to this very much so in the next couple of slides, line of sight, LOS, and this referred to also visual or radar line of sight, VLOS or RLOS. And you'll even hear terms like EVLOS, like extended visual line of sight, for people with very good eyes. No, I'm joking. Okay, we are done pretty much. Just definitions next. Okay, so TLAs will just give you what the letters stand for. In fact, there's 2 others here. ICAO is the International Organization for Aeronautics, and CAA is the Civil Aviation Authority for the United Kingdom. However, we're going to look at how the international bodies or some of the more forward-leaning national bodies have defined what an unmanned aircraft and similar such definitions are. Because even though it would seem simple enough that a UAV is an aeroplane without a pilot on it, they have they've gone further to complicate the issue, as we will see. For example, if we take UAV or UAS, concentrate on the UAV, that's the aircraft itself. The system is defined as the data links, the ground control station, the crew, any other launch and recovery systems involved with that. But the aircraft itself, they are trying to distinguish from other things that fly without a pilot, such as missiles. And they go on to add certain definitions, such as being powered. It obviously doesn't have a pilot. It uses aerodynamic forces, which stops it being a balloon in many respects, and they can fly autonomously or be remotely piloted. And that's important for later definitions. Interestingly enough, though, it can be expendable or recoverable, and its payload could be lethal. But that expendable piece means maybe it doesn't come back. And then we'll see how that actually confuses the issue. On to remotely piloted aircraft. This is now OFA. In fact, ICAO and most of the international organizations are going towards RPA being the term of choice, or RPS. It is actually a subset of UAVs, and this is important because personally, I think this course should all be about unmanned aerial vehicles rather than remotely piloted. The remotely piloted piece means that the aircraft itself, wherever it is, always has a human pilot attached to it remotely. So there isn't there isn't a computer that is autonomously flying it. As we will see, there are many systems out there which are not remotely piloted. They are actually flying on their own. often the smaller systems, but in some cases as large as they come. So everyone, the craze is for RPA, RPAS, but I think we should concentrate on UAV because eventually we're going to come back to this. We're going to realize that humans are often the limitation in these things. And then very recently we have unmanned combat aerial vehicles, and these just, they have weapons on board, but there are very few differences between that and the previous, at least one. Now's the time to start looking at some problems with those definitions. And these are items that either conflict directly with them or just throw up some issues. The first one, which isn't so bad, is optionally piloted vehicles, or OPVs. A number of these have become en vogue of late. The aircraft you can see in front of us here is the Northrop Grumman Firebird, and they're using them to get around access to the national airspace issues. So the aircraft can be flown and certified with a pilot and then flown without one is the idea. And then what we can see in the video is a very good example of one that's fielded in Afghanistan, and we'll see it in action, the Karman K-MAX helicopter. The second conflict is the cruise missile, and we've taken the latest example of the Tomahawk here in the Block 4, and I've expanded one of their sales items, which shows a satellite data link terminal for in-flight communications and a camera system. So you're basically dealing with an unpiloted, or a pilot that's removed from the cockpit. It is expendable, and it carries a warhead, and it can be controlled in flight or flown autonomously. So I'm having difficulties not making that a UAV, but in some respects that's exactly the point. It's why the UAVs are part of the international trade and arms restrictions in the US. They don't want this sort of technology to be exported, and also but it does, counter to that, throw up some issues when it comes to the morals of UAV usage. Many people argue that it's inhumane, that it lowers the cost of entry into a conflict, and the counter to that would be that actually we have exactly that in the place in cruise missiles, which have been around for many years. Finally, a third area of conflict with those definitions builds on the cruise missile example before, and it's a new capability that's coming on in land forces in a surface-to-surface missile role, as you can see in the main picture, called the loitering munition. The Harop at the bottom left, which is an Israeli design that's been used for anti-radar missiles, etc., has basically been upgraded as simply an anti-radiation missile to have a sensor package, EOIR turret, as you can see in the bottom left, and it will loiter for, I believe the Harrop's got a 6-hour endurance before effectively crashing into the target using explosives in its body. But then on top of that, it can be returned to base. The Fire Shadow is a design for effectively a loitering cruise missile that is also being studied in Europe. So these things, I'm finding great difficulty in seeing where the lies between these and a UAS or an RPAS. Right, we're going to go back to making up some definitions rather than arguing about them. So this one is concerning the piloting aspects of unmanned aircraft, and that alone can start a whole argument running about whether they're pilots, operators, etc. We won't do that here. We effectively define two types of pilots involved in UAS. The first one is the EP, the external pilot, shown on the left, and the IP, the internal pilot, on the right. Fundamentally different skill sets, though I'm sure there are people out there with both. On the left, you're looking at a glorified remote control pilot, which is not said in any disparaging manner. It's an extremely difficult skill set, and they are having to land these aircraft visually, normally from the side of the road, and without the utilization of first-person viewing. So you will see these guys out in all weathers, and I wish them the very best. On the right-hand side, though, these are the internal ground control stations, the GCSs, and these are normally flown using cameras on board the aircraft, positioned in the tail or the nose, and giving the pilots either direct control using a joystick in the Predator family, or more often than not using a mouse to click the aircraft and using its autopilot to fly it into certain positions, from which the EP could then grab the aircraft and bring it into land. So it's just to, we'll look at different concept of operations later in the course, but this is just to give you a feeling of the difference between those two. So bear in mind that this is the UAS basics brief. We just want to get some agreement on what we're going to call the various categories, different types of UAVs as we go about. So this is an entire brief later on in the course for types and a separate one for roles. And there are many different ways of categorizing the UAVs, of which there is no international consensus as I record this. They can be called tiers, groups, categories, and it can be broken down by weight, payload, kinetic energy, airspace, integration, etc. This, however, is what I would consider the standard categorization of them, and it's not in any way complete, but it does give everyone a baseline to work from. So, starting from the top left, the UAS is a small unmanned aircraft system. As you can see, they are often hand-launched or bungee-launched. They tend to land or crash in front of you, and you're using some form of external ground control station or a laptop, something that you've carried out into the field. So that's the UAS. Can be both rotary wing or fixed wing. Moving up on the scale, on the top right is the Tactical Unmanned Aircraft System, or TUAS. These tend to be line of sight systems, but rather than visual line of sight, they tend to be almost radar line of sight, a bit like the Falco that we looked at the beginning. This example is the Ranger in Switzerland. They tend to be rail launched or runway recovered, often, or into a net for the slightly small ones. And they carry slightly more significant payloads. Going up in the scale, then bottom left is the male. That is the medium altitude long endurance, and this is epitomized by the Predator type family. The one shown here is the twin engine Dominator XP, known as Centaur. There's various types of it, but it's a conversion of an unmanned DA-42. These tend to be runway launched and landed. They require specific ground control stations and often have in GCS without an external pilot. They either have an auto land system because they can carry a significant amount of payload. And then nearly finally, but going up in the scale, is the high altitude long endurance. A very small category here, but only by number. The Global Hawk is the classic. We're seeing here is I think this one is the Soaring Dragon, one of the Chinese variants, and they have a number. And again, these are runway launched and landed, predominantly autonomous. I mean, they effectively get airborne, do their mission and come home, land and taxi themselves back. They are, as I said, few and far between, but often extremely high altitude due to their design. Then there are the different ones, but UCAV, we talked about their unmanned combat air vehicles, and they tend to be the stealthy, low observable design, jet powered, and the lighter than air. These are a reasonably new category of basically blimps, helium balloons, zeppelins that are also long loiter UAVs. So these are the ones we're going to consider. Next concept I want to explore, for the rest of the courses is one called levels of interoperability, or LOI. In essence, this is how much control you have over your unmanned aircraft. So we start obviously with level 1. Definition is a receipt of secondary imagery or data. And this is basically if the example we have is a command center receiving relayed video. So you're not getting information directly from the UAV, someone's passing it to you. And clearly at level 1 you have absolutely no control whatsoever over that unmanned aircraft or the data you're receiving. Level 2, slightly different. It's a receipt of imagery or data directly from the UAV. And our example would be one of the soldiers holding those remote video terminals or rovers. And they're receiving the video, even in the ground control station, they're receiving it directly from the aircraft. But again, you don't have a say in what you see from that position. Level 3 control, this is where it starts to get a little bit more interesting. You have direct control of the payload itself. And the example, standard example would be the sensor operator can move his control stick and the payload would swing left or right. This is an example of 3 payloads hanging off one aircraft. And 3 people are allowed to have level 3 control of that fitting. It's known as a triclops. But you could also not necessarily use a joystick. You could even have a point and click on a map and the payload would move, and that is still level 3 control. Level 4 control then, something I'm more interested in, and that is where you can move the aeroplane around as well. And they're generally considered to be inclusive. So you can not only move the aircraft, but you also have level 3 control of the payload. So this is a classic one, a mission command element ground control station. You can fly your Predator. But typically, again, either using the joystick or using the mouse, it is the pilot, the operator, that has level 4 control. And then finally, level 5 means you have all of the above, as well as the ability to take off and land, which are excluded from the level 4 control. And I've used the example of the Aryan Scout operator here because, of course, level 5 control gives the impression of this superhero character that can do everything. But actually, it just means you can fly whatever size unmanned aircraft you have. And that could be as small as the Scout, as we saw in the video at the beginning. Okay, levels of interoperability. Okay, we'll just take a couple of minutes to look at the various types of operation, almost the concept operations that many of these UAVs are operated under. The first one is the most basic, visual line of sight. And a lot of the regulations discuss the requirements of visual line of sight with either the pilot in command or even a suitably qualified observer. Interestingly enough, they tend to talk about it needs to be unenhanced line of sight, so you can't be using a pair of binoculars. And if they were to put numbers on it, they tend to say below 400 to 500 feet above ground level, and also within either 1,500 meters or 1 mile of either the pilot or an observer. And in theory, you could space these out and have observers every 2 miles, and they should be able to pass this thing along. But each one of these needs to have a medical, some training, and the rules go on and on. So it does complicate it. In essence, the visual line of sight operations are designed, if you think about the Aryan Scout, they think about maybe inspecting power lines just above you, or looking at structures, or taking photos of an open pit mine, something like that. Visual line of sight. The next step up in complexity and capability in some respects is the radar line of sight system, or RLOS. This is clearly where we're going outside of the regulations of needing a visual ID on the aircraft, and the concept of operations are very different. We're now looking at a local area. In some respects, 50 kilometers even are considered a normal RLOS range. There are systems out there claiming sort of the 200 to 300 kilometer range, and not being a mathematician, I've put the equation up there for the radar horizon range. You can work out which altitude you need to be at. But these photos show an example of just how you can go from the sublime to the ridiculous in extending that radar line of sight by using towers and masts. So these tactical systems are basically a full-up intel surveillance reconnaissance platform, and they're not being used in the local area. They can be launched from their airfield and used to support troops, firefighters, whoever else within that RLOS range. So that's our next capability. Finally, we get to the extreme, which is known as BLOS, beyond line of sight. And there's two ways this can go ahead. The predominant method is by using a satellite communications link, using that domed front that you'll see on certain unmanned aircraft, and that we pointed out in the photos earlier. So a satellite BLOS requires obviously a large satellite dish at one end, and the satellite in position. As we can see here, it's not all as easy as you think. You need to position the dish and the satellite so that they have the same footprint. But there's another way to do that, and that is by what's known as data or radio relay, where you can put a UAV with the right capabilities and antennas in the middle between the one that you want to fly and operate and where your ground control station is. Effectively extended the radar line of sight by using another UAV, and the Hunter MQ-5 does that. So there are systems out there, not necessarily brand new ones, that have that capability. So when we're getting into beyond line of sight, though, we really are talking about a different kettle of fish. This is where you are most likely to have a separation between the launch element and the mission element, as you see here, LRA and MCE. You are dealing with complexities of handovers. You are dealing with complexities of frequency allocation and management. It really is an order of magnitude more difficult and complex. So this is definitely for the bigger systems and needs a significant amount of consideration when it comes to developing ConOps. RSO, remote split operations, is what the US have termed it when you have both the mission and the launch recovery element separated as such. And it's slightly more complicated than that, as this diagram suggests. But needless to say, that is the classic BLOS operation that we see currently. Let's now take a look slightly outside of the UAS itself. Let's look at the external players that are involved in a UAS mission and in some of these ConOps that we've briefly glanced at. So we'll start with our valiant crew in their ground control station, and we will. They have to coordinate with, in this case, a launch recovery element, and the most extreme, if it was a BLOS mission or remote split operations, to ensure that the right aircraft with the right configuration is airborne with the right fuel and going in the right direction. Once this coordination has taken place, then our ground control station crew, who are the mission command element, will therefore have control. And the mission then commences, and there's an awful lot of coordination with their own operations cell, or SOC, Squadron Operations Cell. This is a military example, but we'll look at a civilian one in the next. A typical cell would have a MC, a mission commander, who would be overseeing several ground control stations and the coordination of the entire flight. An image analyst will be working on the video feed, maybe even the sensor feed if using a synthetic aperture radar or other such, and some form of a MIC, in this case a mission intel coordinator, somebody dealing with the various information inputs and ensuring that the crew gets all the intel that they require. But obviously the aircraft is airborne for a purpose, and that is to work with ground forces, is the typical role, and they are known as the supported unit, or the SU. These are the guys on the ground, either using remote video terminals or using just direct radio communications with our UAV, and the mission commences with them coordinating with the GCS, with the MC, etc. But it doesn't stop there. So we have a number of external agencies that are both monitoring the feed from the UAV, normally through that level 1 LOI, but they're down the PED, the processing, exploitation, dissemination chain that we saw earlier on. So, and they have direct inputs, normally through the mission commander, to the GCS to retask the aircraft, to send it to other subordinate units, to send it home early, as you see fit. But you do get an enormous amount of interplay there. On top of that, there are other agencies, other more classified ones potentially, that are involved in the mission. And obviously for a 24-hour mission, there may not be just one supported unit. There may be several, and you may have several roles in each of those. So a lot of people are interested in what's going on and can input into your cockpit, as it were. And then finally, this entire picture is repeated time and time again at all the other UAV units. So other sector operation or squadron operation cells may have something to say. There needs to be coordination with frequencies, with aircraft spares, with replacements, with mission priorities. So there's a lot of coordination going on. And in fact, the ground control station is often referred to as an intel fusion cell, because you are taking so much information in, and mainly because of these external players. That's a look at the military. We're going to come up with a slide now which shows a very similar thing going on, but with a French civilian operation.
Bonjour, attaque à Garon, est-ce que c'est possible de Brignoles?
Le rolling bar, c'est les unités. Rolling bar, les unités sont choisies. Vous êtes bien en place, là? Ok, ça marche.
Je passe en prochaine flight et checklist terminée.
Donc l'avion que vous voyez est un patroller, donc un STEM 15 de fabrication allemande, utilisé pour l'instruction des pilotes. Il a été donc monté en drone et il est utilisé pour ma part, donc j'effectue les décollages et les atterrissages. Je suis pris ensuite en charge par une station sol qui pilote l'avion, et il peut être également utilisé en mode complètement automatique, mais pour des raisons de sécurité ce n'est pas le cas aujourd'hui.
Je crois qu'il y avait les Brune sur l'avant, mais il y va, en direct le feu. Donc ça peut amener une plus-value pour faire intervenir, pour voir les accès, surtout les accès dégagés.
Quand je verse pour le COGIC, donc on va prendre la main là, sur la mission. Donc il faudrait demander au drone qui se rend en kilo delta 62 Lima 5.
Rendez-vous kilo delta 62 Lima 5. Parlez.
Ouais, correct, hein, carrefour de piste.
Vidéo normale. Est-ce qu'on va avec au thermique la chaleur du moteur?
Ici, arrêtez quand il est possible sur le drone, passe une recherche
en longeant la piste, direction plein ouest jusqu'à l'intersection jusqu'au GR4. Correct. Ah, je confirme, le drone suit la piste jusqu'au carrefour avec le GR4.
Alors, bien pris pour la mission, je transmets donc à l'opération de la boule le nouvel objectif.
À la rigueur, c'est par rapport à ce qu'on a là, parce qu'il y a 2-3 tourments et après on peut. Et la maison, voilà. Pour moi, on est là, non? Ah, vous êtes là. Là, on voit tout de suite la différence d'altitude. Là, il y a 2100 mètres pour l'instant. Là, il y a quelque chose là. Là, il y a quelque chose là. Bon, attends, hein, tu les contacts, je vais chercher les responsables. Ouais. Bon, monsieur. Bonjour.
Dérouler l'arcane pour atterrissage. Donc, à moins que vous ayez des demandes particulières, la mission s'arrête là. Parlez.
So we start to draw to a close here by looking at some of the issues that are facing the UAVs. I mean, a basics overview. And the first one, which this is highlighted with a USAF, United States Air Force issues slide, is manning. Currently, generally the UAS community, certainly in the Air Force side, and not so much in the Army though, they are pilots, fully qualified, they're trained, they're aeronautical experts in many respects, but would be highlighted as the light blue in this graph. The green are guys and girls that have been indoctrinated into the UAS community, the RPAS community, with no previous flying experience. Now, this is basically following the US Army model, and in fact repeated by armies around the globe who don't have pilots to operate with. So in many respects, the aeronautical knowledge base of the aircrew is going to go down. But in some respects, we are also looking at training specifically UAV pilots rather than converting manned pilots whose experiences might not be as relevant. So that's one of the issues. The second one is there are going to be a lot of RPAS UAV operators out there. And this is globally as well. So we've only just started to realize how big this iceberg is going to get. And therefore, civilian qualifications which don't currently exist internationally are going to need to be addressed. And each of the individual services are having to address that their manpower scale is swinging, because they may be unmanned, but they do suck in an awful lot of manpower. So I mentioned the civilian license requirements. These are hotly debated at the moment, both around the world, in fact. The consensus will probably fall somewhere close to where the current manned licensing requirements are, which is some form of commercial pilot's license. But we can discuss this later on in one of the separate modules. But that actually means that you are going to have to bring some form of aeronautical tests to the table. So again, this is a question that's up in the air. And without a doubt, the UAVs themselves are getting smarter. The software is in there, and we're going to see a transition from where the crew are physically directing the UAV to where they're monitoring the UAV's mission, to maybe even where they are simply supervising the aircraft, and maybe a number of aircraft, because they are able to do the job on their own, as well, if not better, than a manned, heaven forbid me saying that. And because of the capabilities of even the smaller platforms are becoming astounding. They've flown handheld ones for 9 hours. They recently flew a small system called Penguin B for 54 hours. So, but with this, you're probably going to need less of them because they're up there doing more for longer. And that also means that they may be able to carry more and do more missions. And so actually the complexity of a single UAS flight is going to go up. and therefore the capabilities and the knowledge, skills, and attributes of our crews need to be such that it reflects that. So it really does beg what is the best solution when it comes to the future organization of a UAS unit, both civilian and military. And I don't think the question is out there, but I certainly have posed many of the issues. So having now bigged up the UAVs of the future as these highly intelligent autonomous systems that are utterly reliable, let us tell a little known story that occurred in July 2011 of the delivery of the first overseas sales for the Northrop Grumman Global Hawk, known as the Eurohawk, an enormous beast of an aircraft to the German Luftwaffe, who are using it as an ELINT-SIGINT platform. So the aircraft is leaving Edwards Air Force Base due to Manching, Germany, and it was planned to fly over the States and then cross the Atlantic and then get handed over to the operators who were in Germany and fly down through Scandinavia and into past Denmark. So that was what it was planned for. Unfortunately, what actually happened was when the FAA got wind, even though it had been cleared, that some of the operators were not Americans, they refused to let it fly in US airspace and therefore punted it out into the Pacific until it cleared into Canadian airspace, for which point it was able to fly all the way home. So fly all the way en route, which it did all the way until just north of Scotland, when unfortunately link was lost to the aircraft. And therefore there was a great concern. It could be tracked on radar, it could be tracked by transponder, but what it would do for the first time as it entered European airspace. And actually it followed this route, which was its planned route via a number of potential divert airfields, and it followed it perfectly. And in fact, it landed bang on time, even though they'd sent up a chase aircraft to follow it in. And in fact, we have a short video of the chase aircraft coming up. So this goes to show just no matter how well you plan it, this is these things can go horribly, horribly wrong at this stage of the technological advancement. At the end of the video, then we'll move on to the end of the brief, and we'll have a quiz. Speak to you tomorrow.
Den nicht runterfällt, inverted. Im Notfall haust du unser Gear auch runter.
Thank you for your help, John.
Ja.
You're welcome.
Und 150 unser Gear.
Touchdown.
Okay, well, congratulations. You've nearly made it to the end. So this is the quiz we threatened you with at the beginning. This is simply to check understanding, see if there are any areas that you had not fully understand or skipped over. And should you have any questions on what you've heard, uncertainties or requirements for follow-up, please do contact us immediately on oltraining@unmannedexperts.com. And all of the contact details are at the end of this brief. So congratulations on finishing up the UAS Basics module, and we look forward to seeing you on other modules and other courses. All the very best, and thanks again for your time. Let's finally put a line under the UAS Basics module by reviewing the aim and making sure that we have obtained what we were hoping to do in the last hour or so. We can list all the elements, the definitions and the terms should now be clear, but we will come across more in the later courses and they'll be explained as we trip through. And you've seen a number of different approaches and different ConOps. All will be developed in later lectures, and hopefully you'll start to see what options are available when you start approaching UAS planning and problems for your own, and you can decide on a best fit for that program. So hopefully we have completed the same. Congratulations yet again on completing the Unmanned Experts UAS training course, UAS Basics module. And I hope you enjoyed it. I hope you found it informative, but we will take any feedback, both positive and especially negative, either through the website or training@unmannedexperts.com. Should you have any questions about the information you received here or want to get any of the follow-up, then please do contact us immediately. And thanks very much for your time. Thank you again for your time and attention during this Unmanned Experts training module. Should you have any questions about the content or any follow-up or about the quizzes, please email us directly at oltraining@unmannedexperts.com. For any other urgent inquiries or any interest about other training courses and availability, either go through our website, www.unmannedexperts.com, or call us on +1 334 578 2900. Thank you again and look forward to seeing you for one of our other courses. All the best. Good day.